acting as the cops weren't told that it was a
Yeah. They were like, they freaked out.
Yeah.
All right. Cool. All right. Welcome to our first in-person journal club. All right. You guys should get donuts. I'm hoping that we can do this as like every week, every couple of weeks, or every 2 weeks whenever we do this, we just try a different bakery in the area, which I think should be nice. So I think that means we'll be able to try like 6 bakeries or something before our time here runs out or something. But yeah, so originally I was going to do a presentation on the modern mathematics of deep learning, and then I started reading that paper and I realized I understood about none of it. So then I was like, okay, maybe I should go back and do some of the more foundational stuff. And so I ended up looking at these 3 papers: the approximation by superposition of sigmoid functions, the strength of weak learnability, and a theory of the learnable, which are all like really, really important papers in the field of ML theory and the field of deep learning theory in specific. And they actually, I generally don't really like math. I've made my opinions about math, I think, very clear a few times. And I've often said that ML theory is not so helpful for ML practice. But I actually think that these papers, these 3 in particular, say something really interesting about deep learning and are worth like kind of diving into. I don't know how immediately useful it'll be for anything we work on, but like, we'll see. So there's a 90-second overview of what each of these papers are saying. So the first one, the approximation of sigmoidal functions, basically proves the universal approximation theorem, which is this idea that a neural network is a universal function approximator for some defined space. The second paper is about pack learning, which is the theory of the learnable paper. And that is trying to answer the question of under what conditions will a classifier do something useful when you have like a learned problem? And more specifically, how many samples of data do you need before you can say with a certain amount of confidence that your classifier will do something useful? And then finally, the third part is this concept of boosting, which actually is really important for ML practice, and it has a lot to do with like ensemble networks and things like this, which basically is trying to answer the question, if you have a weak learner, which is a model that can classify something slightly better than random, can you train a classifier that is arbitrarily accurate? It's never going to be perfectly accurate, but it could be like 99.99999% accurate. And surprisingly, the answer to this question is yes, and boosting is the way that you can do that. So we'll go into all of these. This is going to be a lot of math, a lot of proofs actually, and for intuition purposes, I'm going to be skipping over a lot of the like constraints. So there's like some places where it's like, oh, you have to assume that a function is consistent, or you have to assume that you know, something is like equivalent or less than or whatever. I'm just going to simplify in those cases. So it's not going to be an exact proof, but hopefully a lot of these will be like provide some intuition for how these things work. All right, so we're going to start with the universal approximation theorem. I'm going to first go through the proof that was presented in this paper, and then I'm going to go through a proof that's much less rigorous, but makes a lot more intuitive sense to me about like how it works, and maybe will be helpful for you guys as well. So the first thing we need to look at is what a multi-layer perceptron is, which is kind of like the standard ML, the standard deep learning model that a lot of the ML theory folks like to use. And the reason they like to use it is because it's generally very straightforward. It doesn't have like very complex linear algebra. It's just represented as a simple yx plus b, which many of us know is like the equation for like a line or something like this, but in matrix form is actually the equivalent on n-dimensional space. So here we can kind of, this is like the mathematical version of what a multi-layer perceptron is. You can, and for a single layer multi-layer perceptron. So I guess it's not actually multi-layer. It's just, there's 3 layers, I guess. There's the input, then the hidden layer, and then the output, which you can kind of see visually here. So the output of a multi-layer perceptron is the weighted sum of n neurons in the hidden layer. Each neuron consists of 2 parameters, the weight y, and then a bias term theta. And for some input x, each neuron multiplies the input by whatever weight is associated with that neuron, adds the bias, and wraps the whole thing in some sort of a nonlinearity sigma. Some of these nonlinearities, if you've worked with deep learning, you might know, like ReLU or sigmoid functions. This paper is all about sigmoid functions, kind of by the name. But as it turns out, a lot of this stuff will approximate to other kinds of nonlinearities. Yeah, what's up?
Yeah, I never understood like the whole nonlinearity thing. Like, what's the, like, from what I understand, if you don't have like the nonlinearity function as part of this,
yeah,
it can't estimate nonlinear.
That's correct. Yeah.
explain that.
Yeah, so I don't know how intuitive this is to you, but so it's kind of a proof of linear algebra is a sum or any linear transformation over a set of linear transformations, like any combination of these, can be compressed into a single linear transformation. Does that make sense? Is that intuitive?
Kind of, yeah.
So one way to kind of think about this is like, the set of linear transformations includes like addition and multiplication and division and these things. You can chain any number of these together and represent it as any other as a single linear operation, which is much more intuitive when you start working in like matrix spaces. The corollary to this is if you can define if you have a single nonlinearity in this like set of linear transformations, the whole thing becomes nonlinear. And if you're thinking about this in neural network terms, let's say I have like 10 layers of a neural net, and none of these have a nonlinearity on top of them. You could actually write whatever that thing calculates as a single neuron, as like a single linear layer. It just instantly compresses because like it doesn't have any additional capacity to learn anything. So the nonlinearity is actually really important because that's what allows it to learn something that's not a linear function.
So like literally like the function, if the function that it's learning is like totally,
yeah,
then it can't learn it
unless it has a nonlinearity. Yeah.
Okay.
But what's interesting is that like it is sufficient to have like not all nonlinearities apply, but it is sufficient to have a nonlinearity to learn any of these functions. Yeah.
How is something like really non-linear? Isn't it just like flat and then just like?
That is definitionally nonlinear. It's not linear. It's flat and then it.
Oh, so that's what I'm saying.
Yeah. It's like it's linear in a part. It's like it's linear in one part and then linear in the other part. But because it has the hinge, it makes it nonlinear.
Yeah. So linear on a graph is a straight line.
Yeah, on a two-dimensional plane is like a straight line. Yeah.
And nonlinear is anything that's not a straight line.
Yeah.
ReLUs, is that like what you see with like state vector machines where it's got like the hinge? Those are two different things.
I think you're thinking of different things. Yeah.
Okay.
A ReLU is just a specific function that's like 0 for anything less than 0 and 1 x for anything larger than 0. Anyway, this is a multi-layer perceptron. And more importantly, this is a single layer multi-layer perceptron. So we're going to actually make this like relatively simple. We're only looking at a single layer MLP. We're not going to look at like farther like deeper things. And it turns out that a single layer multi-layer perceptron is actually sufficient to be a universal approximator. So like it seems like it would be intuitive that like, oh, if I have a arbitrarily large model that is arbitrarily deep, that would of course be able to model any kind of function. But actually it turns out that in order to model any function on a space of size n, you only need a multi-layer perceptron with a single hidden layer with n neurons. That's it. So let's talk a little bit about what kind of nonlinearities we can actually use here. And this is like, again, you know, hope if you haven't seen integrals in a while. You know. So as it turns out, you can't just use any nonlinearity to solve this problem. And we briefly touched on this. We said like sigmoid functions work, tan functions work, ReLU functions work. All of these have something in common, which is they don't lose information that you pass into it. So what I mean by that is, let's say we were using like a sinusoid function. A sinusoid function is something that repeats at a certain frequency. So if you have x is equal to 0 versus x is equal to, I think, 2 pi, those are the exact same value on a sinusoid. It has that like repeating pattern. That means it loses information. You cannot predict what, if you're given the output of a sinusoid, you can't predict what value of x produced that output, which means on a certain unit, like on a certain space, in a certain metric space, let's say it's like the square of a two-dimensional plane, you can have an integral of that space that sums to 0. It loses all of the information. You have no idea what's actually in it. So those kinds of nonlinearities are not universally functional, like they don't apply to this universal function. You can only use nonlinearities that have this property where when you do the integral over the certain space, it does not, it only results in 0 if the way you are measuring the space is also equal to 0, is kind of what this is saying. And this is kind of important because this is how they end up proving the contradiction. Like this is how they end up doing the proof for the underlying universal approximation theorem. So does this kind of make sense about like how nonlinearities work and like why nonlinearities have to be like information preserving? Okay.
I mean, is it as simple as it, like on the graph again, they don't repeat the y position, or it's not that simple, right?
I suspect for many of the cases that we look at, that is probably sufficient. But the more general term over arbitrary dimensions is this. Because what you're saying is a much stronger definition than what this is saying, which is just saying, if this integral is equal to 0, then that means du dx must be, or du of x must be 0. Or in other words, this integral must be not 0. It must result in something. Okay, cool. All right, so I've talked a little bit about spaces. And like n-dimensional spaces. This is just like a little visualization of like what it means to be in a n-dimensional space. So you can imagine that, this is like a 2-dimensional space versus a 3-dimensional space. This proof is true for n-dimensional spaces, which means you can have an arbitrary finite number of dimensions. A lot of the neural networks that we work with have like the CLIP model, for example, outputs things in a 512-dimensional space. But the point is like it can be arbitrarily large. For most of the rest of this thing, we'll be mostly working in like 2-dimensional spaces because it's easier to like show, but understand that all of this approximates to larger spaces. So, so of course, like this is a function in this, these are both examples of nonlinear functions in those spaces. So like this is a nonlinear function in a 2-dimensional space, it's just some squiggly line. And this is a nonlinear function in a 3-dimensional space, which in this case is like a convex parabolic thing. But you can imagine it could be anything. Like it could be any set of squiggles on this surface, or in this, in the case of 3 dimensions, any like shape or mold that you can imagine. So, and this is like kind of a tough thing to understand. There is a set of functions that you can use to create things on a 2-dimensional space, right? For example, yx plus b is a line, or x squared plus y squared equals r squared is a circle. This set of functions lives in its own space, which is n-dimensional. Where the n-dimensional space where the functions live is not necessarily the same amount of dimensionality. Actually, it's generally much greater than the same dimensionality of the space to which it projects into. So you can imagine that the set of functions on this space is also represented by some kind of space. So let's assume this is like how we set up the contradiction. Our base theorem is that this sum of neural network type functions, like the entirety of neural network type functions, is sufficient to cover the entire space, like all functions that live in this 2-dimensional space. For the point of contradiction, let's say that that's not true. That means that there's some area in the overall space of functions that map or project into the 2 dimensions where that's like a closed subspace, where the functions that neural networks actually do create are in that space and everything else is not the case. So as an example, we might say that you can produce this green squiggly line with a neural net, but you can't produce this red squiggly line with that neural net. Because just by definition, we're assuming that this is the case, that there must be some set of functions that you can produce. If you have a subspace, and you also have a function in that, like it's called a functional technically, but we can just use function here, a function in that subspace, then there's a certain theorem that says that there must be an additional function that operates on the entire space, called L in this case, that mimics the subspace function inside this green space. This is a little bit weird, and it's like kind of hard to like wrap your head around. And I'm not sure I fully understand the intuition behind this in geometric terms. But the basic idea that the way I kind of map this is like, intuitively, if you have a closed section in a larger thing, you have to have some sort of way of identifying that closed section. Whether it be like a circle in a 2-dimensional plane or a rectangle in a 2-dimensional plane, you generally have a larger function that you can use to say, hey, when I'm inside this circle or inside this rectangle, do X, and when I'm outside of this circle or rectangle, do Y. Just sort of like intuitively, this is like kind of how I think of this. So I think of this like as an identifier function, which says when you're outside of this green circle, do whatever. But when you're inside the green circle, you have to mimic exactly what's inside that green circle. So because at the beginning we said that our nonlinearity function has to be discriminatory, which remember we said that the space, the integral of that space on a specific measure has to be equal to 0, then we can further specify the linear functional on the functional space as being 0 inside the green circle and being not 0 in the red space. This is just something that we have that we can just kind of take directly from this equation here, which says the integral over any of those subspaces must be 0. Or we can assume that it's 0. So the problem with this is the point of a discriminatory function is we said if that integral is equal to 0, then that must mean the entire thing is equal to 0. And by this theorem, this like Hahn-Banach theorem, it basically says that this function actually can't be 0 everywhere. It has to be 0. It has to be non-zero in the red space. It can't be 0 in the green space. And so since this is a contradiction, we end up being able to say, oh, the only assumption that we made was that the set of neural network functions can't cover the entire functional space. And so that must be not true. So the set of neural network functions must be able to cover the entire space in an n-dimensional space. Very, very confusing to me. I was kind of able to get there through like thinking about it in geometric terms. But I think this like eventually kind of made sense. And it's okay if it doesn't make a ton of sense, but open to questions here if you have any.
I understand where you started and where you ended. The middle part.
Okay. Yeah.
I believe it. That's us.
Okay.
We'll take your word for it.
All right, great.
So the first half was true. The second half was also true, but because the two things couldn't be true at the same time, therefore.
Yeah.
You have to infer then
that the assumption that we made at the beginning was not true.
Right.
So I will say like there's a certain amount of magic here. Like I don't fully understand this theorem, and I'm just kind of like I didn't like dive into the proof of that theorem, and I feel like I need a much bigger background in set theory to like fully get into that. But this is just kind of like the nature of math, is sometimes it'll just be like, and this theorem exists, and so you can just assume that that's true. Similarly for like this representation theorem, although this kind of is also a little bit magical, but like whatever. There's another proof for the universal approximation theorem. So what does this actually say? This says that for a neural network function g of x, you can get to an arbitrary amount of error, and you calculate the error by subtracting the true function f of x for all values of x in that space, which I think is actually a really powerful idea, because again, it gets at this idea that a neural network can represent any continuous function on its dimensionality with only a single layer. So there are a lot of things that you can represent as continuous functions, like most computer vision tasks, for example. And what's funny is like actually a lot of classification tasks are not like strictly speaking continuous, because you have to break things up into categories. Same with like natural language processing, where like words and inputs and outputs have to be discrete. But as it turns out, you can actually map a lot of these things into a continuous space and then just treat everything as continuous. So that's what embeddings do, right? And so it turns out that the class of problems that can be modeled as continuous or near continuous, and those discrete problems are near continuous, is actually really, really large. And so a neural network which can approximate any of these things on that space ends up being really, really powerful, because you can just take any neural network as a like piece of technology and use that to train or to solve all these arbitrary problems. So this is like the actual proof that they used that was like very rigorous. I prefer this proof, which is like much less rigorous, but like makes more sense to me. So again, imagine a n-dimensional space with some function f of x. As it turns out, a pair of neurons in a neural net can approximate a pulse function on the two-dimensional space. So what is a pulse function? A pulse function is just something that basically goes up, stays up for a little bit, and then goes back down. A sigmoid function is a nonlinearity that we talked about that has the property that when x is really, really, really large, the sigmoid returns something that's really close to 1. And as x goes into infinity, the sigmoid returns 1. It has the other property that as x gets really, really, really small, or something less than 0, it returns something that is approaching 0, and at negative infinity results in 0. So it has this like S-shaped curve. If you have a neural network like this with some really, really large weight associated with it, that is like kind of like a step function. Because what is a step function? It's like this, it basically just goes straight up in like an infinitely small space. Well, as it turns out, that's kind of like what a sigmoid is doing when x is really, 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 really large. So if you take the input x and multiply it by some really large number, by just having the weight being really, really large, then you can approximate to some amount of error a pulse function. And you can do this with any pair of neurons. So one of them is the pulse that shoots it up, and then the other one is the pulse that brings it back down, or the not pulse, the step that brings it back down.
Why does it matter? Like, why is the pulse function relevant here?
Well, I'm getting there in a second.
Oh.
So just know that with any pair of neurons, does it make sense that with a pair of neurons, you can create a pulse function on a two-dimensional space? Yeah? Yes? Great. So the reason a pulse function is important is because it turns out that you can do this with any pair, any number of pairs. So if I have 20 neurons, then I can create 10 pulse functions. If I have 40 neurons, then I can create 20 pulse functions. And these pulse functions can all be of arbitrary size depending on what the bias is. So the bias term, that x minus 1 here, is what determines how big or small the pulse function actually is. And really, it's actually the difference, like, it's kind of implicit here, but this is saying like 999x plus 0. So the bias there is 0. So it's actually the difference between like the bias term here and the bias term here that determines the width of the pulse function.
So it's like you're so it's kind of like you're taking the curve and you're showing tiny chunks.
You're following, yeah, you got there, exactly. The sum of many arbitrarily small pulse functions is a Riemann sum. If you've done, introductory calculus, you know that Riemann sums can approximate any function QED.
That's where I've heard that thing before. That's like we learned about the universal approximation theorem and calc 2.
That's maybe. I don't know, maybe.
Okay.
I haven't taken calc in years. But yeah, like if you remember any calculus, hopefully I don't have to prove that the Riemann something is true, but like it should hopefully make some intuitive sense, right? Like you can just, as the limit gets smaller and smaller and smaller, these squares become smaller and smaller and smaller, and so you can eventually at the limit approximate that, perfectly capture that function. But since this is an approximation, we can approximate that function almost exactly. And more importantly, you can approximate it to an arbitrary level of accuracy. So it is finite, like you can't ever get perfect, but because you will always have like these rectangles will always have some width associated with them, but you can make it arbitrarily small. And so they end up being like universally approximated. So this is what made a lot of sense to me. That it's like not technically rigorous, but it's like, I think it's like a much better like visual proof that explains like why neural networks are able to approximate any function that you throw at it. Okay, so that's like the first paper. Hopefully that was like not too bad. Any questions there about any of that?
Is it like less to approximate a nonlinear function using basically like a cascade of pulse generators?
Yeah.
Is it less information?
No, so yes, it is less of information because it's an approximation, but like you can make the information loss arbitrarily small.
Right. Interesting.
Yeah. Now, that's not to say that like this mechanism of using neural networks is not very practical, because you don't want to have like a million pairs of neurons that each like represent a pulse function that small. But the point is that it is capable of learning that function. And so you can imagine that some complicated combination of linear operations with these nonlinearities on top is capable of learning the same function with many fewer neurons.
So like,
but we don't prove that down because we don't care.
So like in theory, according to this, if you have a super complicated two-dimensional function,
Yeah.
eventually you just need to add more neurons and then
Correct. Eventually the neural network will be able to approximate it.
So yeah, so like any function, so the limiting factor is literally just how many neurons are in that.
Yeah. And
It's
so
only one layer.
it's only one layer, yeah.
So you only need multiple layers when you're dealing with more than two-dimensional.
Well, so it turns out that like if you only have one layer, like you can approximate any function, but at some point, like in practice, you'll run into problems with like memory. And so the next thing that we're going to talk about is like how many data points do you need in order to train a function like this? And so that's pack learning. So this is a paper that came out of from Leslie Valiant out of the University of Oxford. And he's a really cool guy. I actually got to work with some of his PhDs. So not him, but I got to work with some of his PhDs. So that's like kind of the same, maybe, I don't know. But he presented this paper in 1984, and pack learning stands for probably approximately correct, which is a framework of defining like what kind of problems you can actually use deep learning on, like deep neural networks on, and like how many data points you need in order to get certain confidence bounds that the model will actually be useful. So I think the idea behind probably approximately correct is actually fairly intuitive. A standard classification task involves some data X and some labels Y that represent some distribution. We want to find an ideal model that, given an input from X, returns the corresponding value Y. Now, ideal models aren't possible because you cannot, we just said by the universal approximation theorem, you can't perfectly model any function. You can only get like arbitrarily close. So there's two caveats here. Well, the first one is that the model can only produce approximations. But the second one is we're adding another layer of indirection here because we aren't giving the first model the full function. We're just giving it a few training points off of that function. And so it's possible that the training points, actually it's very likely, that the training points don't fully represent the full distribution. The class of functions that, given a set of discrete data points on a certain distribution, the class of functions that technically could represent that, that set of data points is infinitely large. Does that kind of make sense? I'm gonna let that pass. Okay. So given a set of discrete data points, like let's say I had a number line, right? Or like just a linear line. We can pick like all of the points where X equals Y would be explicit data points on that function. But it turns out that the class of functions that also fit all of those data points is infinitely large because you could also have some squiggle that just happens to go up and down and hit all those data points. So you can't ever predict with 100% accuracy that your training data is going to perfectly model the distribution. So there's two layers of indirection here. The first one is that we know our model is only going to be true to some amount of error for a neural network. And the second one is that depends on the training data being good. So pack learning kind of formalizes this idea. As we see more training data, the likelihood that the model that we have is a good approximation goes up.
Is it why like I'm like a neural network might be like might have a really high accuracy for something, might be doing it completely like wrong. Like
Yeah. So this is we're overfitting, right? So we're going to talk about overfitting in a bit, but like exactly that. A neural network could overfit on a training set and basically predict the wrong function for what's actually there. And in fact, like most neural networks aren't predicting like the right function, right? Like they're always going to be a little bit off, and that's definitely a function of like how much data there is. Okay, so we're gonna like tackle.
So before these papers, like all these like machine learning researchers were trying to find like perfect fits. These guys
No, there's like other theories of machine learning out there. This is like specific to neural networks, and it's a reframing of a different model. Like I think that's like called consistency or something like this, like the consistent models or something, which we'll actually touch on in the proof for pack learning a little bit. But like, no, like it's not like people were just kind of doing things blindly, or what you said was like trying to find perfect fits. Like I think like. Yeah, I think that like the theory was that you probably can't find a perfect fit, but there was some like I think some of the Gaussian mixture model stuff was actually like kind of in that direction, but it's like a lot of the statistical methods, which like for various reasons don't matter anymore. Anyway, okay, so we're gonna like talk about each one of these words independently, and then we're gonna get into a proof. So in probably approximately correct, we're gonna start with approximately. So we touched on this idea of approximately correct with the universal approximation theorem. A model is approximately correct if its error over the set of inputs is bounded by some value, where that value is less than like totally random. And what I mean by that is exactly this idea of like what we saw with the Riemann sums. We can't ever get to a totally perfect value, but we can get arbitrarily close. And as long as that arbitrarily close thing is not like totally random, it means that the model is approximately correct on that function.
Let's one of them say it because I think we're getting drinks. Can I get you some?
I'm good.
So it's better than flipping a coin. We know it's better.
For a binary classifier, yeah. And you know what's interesting actually is like it's only like this is only it's only not approximately correct if it's exactly random. If it's like a little bit on either side, then you can just flip it, right? Yeah.
So it's like totally wrong every time.
Then it's still right. If it's totally wrong every time, it's actually right.
It's a big deal.
Yeah. There's actually like there's a funny like concept in like the stock market, which is like somebody who can predict stocks exactly incorrectly is just as valuable as somebody who can predict stocks like perfectly correct. Are you good, by the way? Okay, cool. So there's one other thing that we're going to assume here, and we're just going to take this as a given. I don't think it's like a terribly hard constraint, but basically we also assume that our models are consistent. And consistency here has a specific meaning, which is it can memorize the data that they've seen in the training set. So it doesn't mean that it has to memorize. And in fact, for most generalization cases, we don't really want it to perfectly memorize, but it can. It has the capacity of doing so. Okay, so that's what the term approximately means. We're looking at models that are bounded within a certain error and they're consistent over their training set. So what does it mean for something to be probably correct? Well, a training regime with some points taken from the distribution won't produce a model with specific error 100% of the time. And this is because if you're randomly selecting data points, then the models that are produced from those data points are going to be different. And they're going to be different as a function of the random data set, like the random data sampling. Even if your learning algorithm is entirely deterministic, which I think neural networks actually are, except for their random initial condition, because you're sampling your data randomly, they're not necessarily going to get to the same value every single time. And so, we can actually formalize this a little bit more mathematically. A learning algorithm L will output a model with a specific error E over a distribution D with some probability delta. We're just like assigning variables to these terms that we already kind of understand intuitively. And we kind of have this like little image at the top, which is basically saying, look, as you change the data that you pass into the learning algorithm, you're going to get different functions that the model thinks is correct. And these different functions will all be bounded by some error, but none of them are going to be perfect. One thing to note is, again, this is kind of just an assumption we make. And it's not, I think, an unreasonable assumption. We assume that the total possible space of the models that we can learn is finite. It might be like, so it might be like really, really, really large, but it's still like a finite space. And so here you can kind of see like, okay, imagine you have this true distribution D. Well, all of these other functions are like kind of related to D, but like they're off by like slight parameter changes or whatever. And so they're bounded by some error. So we have the approximately, which says models are bounded by some value. By the way, one thing to note about like approximately is like, again, a sinusoid function would not be an approximately correct value for D because the error is not bounded. The error is totally random against like whatever the function is. They aren't related at all. What? So like a sinusoid is just like a squiggle, right? Like it just goes up and down. It has no relation to the actual function you're trying to learn. So the error across all of X is not consistent.
So like if you look at
here?
No.
I'm just bad at drawing sinusoids. It's supposed to be like a regular repeating pattern.
Yeah. Sorry. I thought that the red one was the.
No, the red one's the bad one.
Okay.
Yeah. Okay. So this is I think the most interesting part of this of pack learning, and it's also the thing that requires the most proving. If a concept is pack learnable, like if you have a classification task that is pack learnable, that implies that you can bound the number of samples that you need for a specific error and a specific delta. In other words, if I sample m data points, I am guaranteed with a likelihood of delta to get a model that produces an error approximation of E. So it's probably approximately correct. There's a probability that I will get a model that approximates this function. And yeah, so in other words, I can get a model that is E away from the true function delta % of the time using m samples. The fact that you can bound this at all is kind of interesting to me, because it's saying that like, hey, if you have like, you don't have to sample like infinitely. Like there's a specific number of samples that you need to grab, which will do the thing that you want. And so we can like, first I want to just like talk a little bit about the intuition behind this function here. So the first one is, as the error goes up, the number of samples that you need to grab also goes up. Or sorry, let me rephrase that. As the error goes down, the number of samples that you need to grab goes up. So this is what we were saying about the like universal approximation. Hopefully this kind of makes sense. Like as the model gets closer and closer to the function that you're trying to approximate, you need more data points. So if I want something that is like, has an error of like 0.9, I need fewer data points than a model that has an error of like 0.99999. Or I guess I really mean like 0.00001. Right. So if the error is 0.1, I need fewer data points than if I want to make a model that is like 0.0001. Similarly, as delta goes up, the number of data points that you need M goes up. So what that's saying is if I want to be really sure that the model I produce has a specific error E, I need to make sure that my data, the training data that I grab is as close as possible to the original true distribution, which means I need more data points. And finally, and this part like we didn't really touch on, but like we'll touch on it briefly here, H here represents the total possible number of models that there are for a problem, which in some way can kind of define like the difficulty of a specific concept. So a concept is considered more difficult if it has more possible models that can be used to represent that concept. As H goes up, M goes up. So if you have a much harder problem, you need more data points in order to solve that problem. And this kind of naturally, like this is maybe intuitive when you start thinking of H as like a proxy for dimensionality. So in a two-dimensional space, the number of models that you need is a lot less than if you're working in a three-dimensional space, or a five-dimensional space, or a 200-dimensional space. And so simultaneously, the number of data points that you need in order to get a certain guarantee is also a lot less on a two-dimensional space. Okay, we're going to spend some time actually proving this. Actually, what time is it, by the way?
4:15.
Okay, how long did I say that this is going to go?
4:30.
Cool. All right. So the proof for this is actually like, it's not so bad. We'll walk through it. All right. So because our models are consistent, which we remember what we said, consistency here is like the model can memorize the training set. The probability that a given model is off by error E is equal to the probability that that model can represent the training data and is also off by the error E. That's just like a definitional thing, because we said at the beginning that because it's a consistent model, it has to be able to represent the training data. So we could just define the probability that this model is off by error E as the probability that these two things are ANDed together. Of course, by intuition, the probability that a specific model is off by E has to be less than the probability that any model that exists is off by E. So we can define a small like an error bound here and say, okay, this probability on the top is less than the probability at the bottom, because the likelihood that there's some model is going to be higher than the likelihood that there's only one. Well, if you have a thing like this, if you have a bunch of like or conditions, like the probability that this is better, or the probability this is better, or the probability this is better, you can sum all of those together and get a even better probability bound. So you can say when you have a bunch of or probabilities, you can get the upper bound by adding them. And so we say that for all of the models, the probability that a specific model is off by a certain error is going to be less than the probability that all of the models that exist are off by this error, but we just represented that as a sum instead of as this like symbolic notation. And then here's where we can actually apply the definition, like the mathematical definition of consistency, which is the model is memorized the training set. So we can re-represent this like the model is consistent as the model is consistent for a value x1, the value is consistent for a model x2, x3, all the way to xn, where C is the original data point and the output of the model is equivalent to that data point at that training point. So far, so good? Kinda, yeah? Okay. Well, you have a bunch of probabilities here that are all represented as ands. And when you have two probabilities that are ANDed together, you can represent this as a multiplication. Okay. Yeah, so this is the top part is just like a summary of like where we are so far. Because you can represent this as a multiplication, you can then say, we just compress all of this and we say, okay, for all of the data points inside of a set, a total set of size m, the probability is represented by this term here. Because again, you're ANDing these probabilities together, so it's just multiplication. And because these data points are taken at random, we define the data set as like, this is a random data sample that we're taking, and they're all IID, so they're all independent of each other. The multiplication doesn't have any additional terms. You can just compress it entirely, because it's the same probability for all of them. Does that make sense? I feel like I'm starting to lose people. All right. So as it turns out, because these models are off by up to an error E, which is again something we defined as like this class of models that's having this property, we can write the multiplication of probabilities as a series of error bounds that have to be less than the total possible error. So at any given point, the model is only going to be off by up to E, which means the total multiplication has to be less than the sum of 1 minus E for m times, where m is the size of the training space. And we briefly defined this thing B as a subset of all possible models, but we can just replace that with the total set of models, and again have this like less than sign, because if you have a subset of a space, the probability that something is going to be true in the subset is going to be less than the probability that's going to be true in the entire space, which is the same thing that we said before, less than or equal to, because you're increasing the space and having a bunch of ordered conditions. So the final, we're pretty close to the end. This one, you'll just have to trust me on. 1 plus x is less than or equal to e to the x. That's just a mathematical truism. So we can replace this 1 minus e to the m with e to the minus error m. Which, as it turns out, if you just define this whole thing as being less than or equal to the delta function, and then do the right math with your log functions, you end up calculating that m, the total size of the training space, must be greater than or equal to this thing on the side. It's a little bit weird. I don't have like a great intuition for the overall thing, even though I do understand each individual step for how we got there at the end. I think what's hard about this proof is that you start with this like concept of like, what is the probability that a specific model is bad? And you end up kind of proving something completely different than what you started with. But I don't know, that's just math. Does this kind of make sense?
Well, the step back was, because it's is it that like more data points will get you a more accurate prediction, and this is just the math proof of that? Or do you train differently? Do you use this math in your?
So no, you don't actually use this math at all.
Yeah.
Which is why, like I've said multiple times, that I find the math of deep learning to be woefully inadequate. So what this is saying, it's saying two things. It's saying, one, what you said, which is like, this is a formalization of the idea that as you add more training points, your error for a specific model will go down, and the likelihood that you will train a model of that class will also go up. So it's a formalization of that. But it's also saying the opposite thing, or like the corollary to this, which is if I wanted to train a model with a specific error, with a specific likelihood, then I need this many data points. Nobody ever does that, right? Nobody ever walks into a room and says, all right, I need to train a model that has 0.001 error, and like this, well, actually, I don't know. I could imagine that like there are cases where maybe people actually are doing something like that, but in modern deep learning, that's certainly not the case. But you could imagine a situation like maybe like NASA needs a certain statistical model, like a weather model, that's like, I need this to be of a certain precision or lower, and I need to guarantee that I'm going to get that X% of the time, so it doesn't take me forever. How many training points do I need? That's kind of the idea. I think practically in deep learning, a lot of that is just kind of like, oh, that's interesting. But this lays the foundation, both of these proofs lay the foundation for some more complicated stuff that comes later. So, and actually, this one is actually kind of important. So the pack learning stuff that we just covered actually directly leads you to this idea of boosting. So when Valiant proposed pack learning back in '84, he had this question, which was, if I can learn, let's say I have a binary classifier, it's just like predicting coin flips or something, but like weighted coin flips because it can't be random. Let's say I have a classifier that can beat random like 51% of the time. Like it's just a little bit better than random. Does that necessarily prove the existence of a model that can learn arbitrary levels of accuracy? And I think this is a very cool question. In some ways, I think it's like a very unintuitive, it has a very unintuitive answer, which is yes, you can. So the reason I find this unintuitive, at least to me, is because it doesn't seem obvious that like, if you can do something kind of shitty, you can do it really, really well. Like that doesn't like seem intuitive to me. But as it turns out that not only can you do this, but boosting is also an algorithm by which Like there's a specific way that you can do this such that you can ensemble a bunch of really weak learners and basically stitch them all together and produce something that's much, much better. So ensembling is actually something that is used a lot in ML practice. And it's something that like pretty much every Kaggle model that ever wins uses some ensemble or like some mixture. There's a bunch of different versions of this. There's like mixture of experts. There's AdaBoost. There's like AdaGrad. No, AdaGrad is a different thing. That's a gradient descent model. AdaBoost, there's obviously like the kind of like maximal boosting, which is like the original proof. But in general, ensembling has proven to be very, very powerful. And to me, it's very intuitive that this would be the case. So I'm not actually going to go into the full proof for this because I think it's intuitive enough that you don't need to. But we can go over the mechanism by which boosting works. So boosting basically says, let's say I have a really weak classifier and some original data set. And the classifier is able to correctly predict only purple things, right? All right, so then what do? Well, we take all of the things that it is able to correctly predict and we remove those from the training set. So now it doesn't have its edge anymore. It's not able to predict purple things anymore because there are no purple things. So then it learns something else and it says, okay, well now I'm going to be a weak classifier in some other color. Maybe I learn only orange things or like orange and yellow things. So you do this process again. You say, oh, great. Now you know orange and yellow things. You remove all of those from the data set and you learn another thing that like, again, like is some sort of weak classifier. And you keep doing this until you have a set of weak classifiers that have learned over the entire, like to arbitrary accuracy, that have learned like a bunch of different properties of the data space. Each one of them with only like a 51% accuracy, like something that's slightly better than random. And it turns out that when all of these models agree on something, like on some sort of a classification, that is a significantly more stringent or more strict error bound than what you would get if you had each one of these individually. So you just combine it. You just say, okay, well, if this model and this model and this model and this model and this model all agree that this is a blue dot, then it must be a blue dot with some level of arbitrary error. Because of course, like each one of these models might still be off by a little bit. But you can continually add more classifiers such that you get a arbitrarily strong model, which proves our pack learning thing. The actual proof for this is really complicated, and it's like 3 pages, and I don't think it's worth getting into.
So this implies that if you had a jury of arbitrarily large size, you could eventually get to a totally justful, like criminal justice process.
Yeah, sure.
If every single person on Earth was in the jury.
Assuming that people are assuming that an individual person is like a weak learner, yeah.
A weak learner, and that they have like a strong point of view of one aspect.
Like one. They don't even have to. The thing is, they don't even have to strong point of view. They just have to be like slightly better than random.
They have to have like some point of view.
Yeah, they just have to be slightly better than random. Yeah, I think that's really cool. So boosting is actually something that's used a lot in modern day ML because there's a lot of cases where it's really, really hard to learn something that's perfect, but it's really easy to learn something that's shitty. And so you just learn a bunch of things that are shitty and then you combine them. The most powerful out of the box machine learning algorithm for a limited set of data points is it's this thing called AdaBoost, which is like an adaptive boosting mechanism. So AdaBoost basically takes this and says, instead of like we will specifically sample certain areas of the data set that we know we're bad at instead of just like randomly sampling, but like removing parts of the data. So it's like, it's much more efficient and like actually usable. Like this is, the problem with this is like, this could potentially take like, as you add more classifiers, the likelihood that your random sample actually represents something that like is new is tough. It becomes harder. So you have to wait much longer for each random sample to actually be the case. Whereas AdaBoost basically skirts around that by saying, hey, we can adaptively sample our data so that it's not like necessarily IID. But this is like the most powerful out of the box, like assuming you have nothing else to start with, is learning gradient boosted decision trees with AdaBoost, which basically says, hey, I'm going to learn a bunch of like really weak if-else statements and then just combine them into a forest.
Cool.
Okay, so this is like the foundations for deep ML theory, and almost all of these papers came out in like the 80s and the 90s, and deep learning has come a really long way. And I think that there's a lot of like really open questions that we basically don't really have any good answers for that I was actually hoping to cover in that Modern Mathematics of Deep Learning paper, but I didn't quite fully understand the foundation, so I'm hoping to get there later. But I think they propose a couple of questions. These are the ones that I think are like kind of the most salient. The first one's like really important. So in pretty much every other machine learning program or application or like method, you notice very quickly that as you increase the parameterization of the model that you're using, the likelihood that the model will overfit gets higher, which makes sense. And you can kind of see this with, this is like the thing that we were talking about earlier, where like if you have a set of training points, you might just end up with this like random squiggle that just happens to go through all those training points. That's called overfitting. For some reason, deep learning doesn't show this. We have like GPT-3, which is like billions and billions and billions of parameters, and it's seeing more. It has more parameters than it sees data, but still it doesn't overfit. So that's really weird, and we don't really know why that's the case. The second thing is we have no idea what depth does. All of the proofs that we talked about apply to like single layer neural networks. Like, why does adding more layers even matter? Why do we do this? Like, clearly, empirically, it's much, much, much better. But like, why? We have no idea. And as a corollary to that, like, why do specific architectures work for specific problems? Intuitively, I can understand like, okay, convolutional networks work better for images because it exploits like some geometric constraints. Transformers maybe work better for text because it's able to like learn recursion. But like, there's something unsatisfactory about this. Like, we're going from the architecture backwards instead of going the other way. We want to be able to say, if I have a problem of this kind, an architecture of this form will be better. And we can't do that. And then the third thing is like, standard gradient descent works really well. But like, stochastic. Stochastic gradient descent is a mechanism of saying like, hey, I'm just gonna like randomly shoot around and like just follow the gradient at every point of the curve, and hopefully I'll reach some sort of a minimum for like a loss function where the loss function is arbitrarily defined. Theoretically, that should only work when you have a convex problem. What a convex problem is basically one where the manifold of the loss function is a bowl. And the reason for that is because the local minima is also the global minima. So if you were just bouncing around randomly and going down, then eventually you should reach the bottom. The bottom being globally like perfect or like optimal. But it turns out that actually standard stochastic gradient descent seems to work on arbitrary problems, and that doesn't make any fucking sense. There's actually one thing here that I didn't add that I think is worth mentioning. Another problem that a lot of ML models kind of fall into is something that's known as the curse of dimensionality, which is as you start working with higher dimensional data, the amount of parameters and the amount of like compute that you have to use rapidly becomes intractable, because the kinds of statistical modeling that you're doing just involve integrals that are really, 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 really large, or whatever. Deep learning doesn't have this problem for some reason. We can say, yeah, like, we're using like a 512 dimensional clip model, or like we're feeding like a 10K by 10K image into like a computer vision thing. 10K by 10K is like, what is that? Like several million parameters, like several, possibly billion, I think. Like, it's just a huge amount of dimensionality. And yet for some reason we have models that we can actually run on computers that exist in this universe. So that's like also really non-intuitive. So even though these foundational papers provide us with some theory that I think is like actually really interesting and suggests a lot of like really important things about neural networks, in practice, it's just not sufficient to like actually be informative for like what is going on under the hood. And I think there's like a lot of work that has to be done here. So like the depth question, for example, is like, there was a paper that came out. I say paper, but really it was a book. It was a 500-page proof from Facebook that basically said that the complexity of a model is related to the ratio of the depth and the width of the layers. Like 500 pages just to say that, which is not great. So yeah, and I'm not going to be reading that anytime soon. But yeah, so there's a lot of work that's still going on here, and I think that like probably we're not going to see like a full theory of deep learning anytime soon. But there's some interesting stuff that's happening in the space of the theory that like might actually be useful, like in the same way boosting was useful. And so hopefully in like 2 weeks I'll be able to read that paper, and then I will be presenting on that hopefully soon.
Isn't it also a feature of stochastic gradient descent that you update the weights for each new piece of data that you feed through it, rather than iterating across the entire data set and then updating the weights?
So, okay, so there's—
Does that question make sense?
Yeah. So there's gradient descent and there's stochastic gradient descent.
So gradient descent is like you iterate across, or you—
Gradient descent is like when you look at the entire data set,
and then you update the weights once and do the entire data set again.
Right.
Stochastic, you update on every single—
well, you update it on a mini batch.
Okay.
Which is sampled randomly. That's why it's stochastic.
Yeah.
So the idea is, even if the mini batch isn't like a perfect gradient. Like it's not like perfectly pointing you to the exact optimal place that will get you to the bottom of your loss function. It'll be in like roughly the right direction.
Yeah.
And so you can kind of like go, ooh, and then eventually hit the bottom.
So you get into the local area of the minimum faster, but you can't necessarily convert.
No, it's not.
to
No. You'll get there slower.
It's stochastic.
You'll get there slower with stochastic.
Oh, really?
All the time, you'll get there slower. The difference is, for some data sets, you can't hold them in memory. So people use mini batches.
I see.
Yeah, because like if your data set is like the corpus of all of the words on the internet, you just can't hold that in memory. So you use a batch, like a small subset of that.
I see. And then the point is that it still works.
The point is that it will eventually get you to the bottom.
I see.
But
So
in terms of like
something
actual
pushing-
computation, like raw compute, if you could hold all of that in memory, like assuming an idealized computer that has like infinite space and infinite memory and whatever, the actual amount of computation in terms of like CPU cycles that you have to do is less in the full gradient case.
And so in the case of stochastic gradient descent, the larger the batch size, the better.
Yes, that's actually correct. That is 100% correct.
Interesting.
And so this is like why in some ways TPUs are really cool, because TPUs are like, hey, you want to use a batch size of like 10,000? Go for it.
Okay. Interesting.
But on GPUs, you have like 16 gigabytes of VRAM or whatever it is, so you can't do that. Yeah. What?
I can ask a question. I think there was more.
No, go.
The non-convex bullet, I really understand it that much. Like, why does it work even on non-convex bullet? What do you mean by?
Yeah, that's a good question.
Well, aren't all? What's a non-convex bullet?
What is a non-convex function? Like, well, arguably, like a lot of like the common like traditional deep learning tasks are non-convex, but I don't know if I have like any intuitive examples off the top of my head. Like
a convex problem is like there's like a mountain and the stochastic gradient is like I don't know.
sure, like yeah, going to the top or going to the bottom, yeah.
Okay, so what's a non-convex?
Let's say one that was 2 mountains.
So it's like.
There's like a peak and then there's like a bigger
Yeah,
peak.
it's like if one of them is slightly like higher than the other one, you can get stuck on
Oh.
one that's set.
So non-convex just means lots of local minimum.
Well, no, non-convex just means anything that's not a bowl, or in your case, a mountain. It's just like, so a non-convex function is anything that has more than one maxima or minima. A convex function is one where like there's only one point that is the maxima or minima, and that so the locally maxima or minima spot is also the global minimum.
So I'm curious if like, so like I posted some about like how there are these two like mathematicians who wrote a paper about how like maybe the reason why neural networks work so well is that the like most of the functions that define the physical world are actually pretty low like dimensional. Like there's like if you look at like the most of like the equations they use for this, it's like maybe like to the fourth, but like no, like not really like you don't get like
They're like polynomial time, yeah, like a lot of them are
Yeah,
polynomial, yeah.
Right.
So there's like one part of pack learning that I didn't quite get into, which is like there's a like one of the things that kind of they clarify is like something is pack learnable only if it's also like doable in a polynomial time. But yeah, anyway, to your point, yeah.
But yeah, so like maybe the reason is like they were postulating that maybe the reason that and that neural networks are so good is because they're not actually calculating as complicated functions as we do. But I'm curious, like that was the.
But you would expect to see like overfitting in that case. I feel like even more dramatic overfitting than we don't already see. I think it's a good question. I think it's like reasonable.
Wait, let me give my question.
Yeah.
So my question is like, I wonder is there any research about like, you take a function that like where we know what the function is, and then we like we get the outputs like of the function, the inputs, the outputs, and then we say, hey, neural network, match, like find it.
Sure.
And like have people done that with like different types of crazy functions? Like let's say we take like x to the 10th plus 2x to the 5th plus 3x to the 9th.
Yeah, sure.
And then we know the numbers, we know the exact answer.
Yeah.
Right? And then we see how hard it is for the neural network to calculate. Like why don't we use something that we know and then see if it can match it?
So the answer is the neural network can match it. We know that because of the universal approximation theorem.
Right, but like.
But I don't know that I don't know that you can gather that much insight from empirically observing models mimicking functions.
But then, like, what that wouldn't give us any more insight into like why it's able to estimate non-factors. Like, can we like see what?
I don't really think so. I think like
Can we like watch it like learn?
yeah, you can, and people do that, but like I don't know that it's. I don't know.
Yeah, like, because like one thing that I really like is like with comments, like it's cool that you like if you're like trying to like it with like evidence, like if you can like stop at every layer.
Yeah.
Or like every like training iteration.
And you can see like what it looks like.
Yeah, you can see like what it's learning. You're like, oh shit, it's like look at the cat's eye.
Yeah.
But like, so like I wonder if like the reason, like maybe like we just need to be more patiently like looking through step by step, like what's actually being learned.
So I think that, yeah, I think this is probably not sufficient. I don't have a mathematical reason for why this isn't sufficient. But I will say that every machine learning researcher basically spends their entire working hours and many of their hobby hours staring at the interior layers of a neural network, trying to like parse what's happening. And there are signs that things are going wrong that like if you've done this enough, you can kind of pick up on. Like for example, the weights are getting too large. Like it's not immediately obvious why if the weights of a model of a specific layer are really, really large, that the model is doing something wrong. Yet, this is something that is proven true over and over and over again. So maybe there is like there's probably a theoretical reason for why this is true, but it is not possible, at least I can't really, derive backwards from saying, the weights are really large, therefore this, or whatever. But what you're saying, like that kind of empiricism is something that every machine learning person does all the time. Like actually Sarah and Robin, like the very first thing I told them to do was like, take a small set of data and just memorize it. It's kind of exactly what you're saying. So I don't know. Like the answer is I really don't know. Yeah. I actually think like one other possible answer that I thought was kind of interesting. Some mathematicians proposed this, and again, I think it's very easy for people to propose things without like proving them. But like one of the things that I thought was kind of interesting was like actually it turns out that as you increase dimensionality, it's more likely that something becomes convex because with each additional dimension, you have another way that you can kind of go down. But again, it's one of those things that like maybe I don't know. so like the idea is like imagine you had like a two-dimensional like parabola, right? Like you've reached the bottom. If you add a third dimension, it might turn out that actually there's a way to go farther down, like in that third dimension. And so like if you're like dealing with like 512 dimensions, it might turn out to be that like actually by the time you reach the minima, like the local minima of something in that 512 dimensional space, is so close to the actual minima that it doesn't matter, or something like that, you know? But like, this is all conjecture, like all of machine learning.
It's cool that, like, I think we think of it as like, in like a marble, like running down the wall or something, like such a like physical, like.
Yeah, I mean, people think about deep learning in a lot of different ways. I think like everybody has a different model for it. My personal model, and I think this is the one that you guys are exposed to, is a very geometric based one. Like when I think about something 512 dimensions or whatever, I actually in my head am like visualizing a manifold that exists in that space or something.
You gotta jump into a thing.
Oh yeah.
All right, guys, thanks so much. Please eat some donuts. And I think, who's up next? Let me just check who's up next. Is that really true?
The only feedback that I have for you, Amol, is please use the SUT formatting for presentations.
Robin, I have you or Sarah scheduled next.
Really?
Yeah. So you guys can fight. You guys can deathmatch over that one.
Mm-hmm.
Let me pause this recording.